Types of forces and applications of Newton's laws of motions. Here we have two main points. The first point is types of forces, and the second point is applications of Newton's laws of motions. Let's start with the types of forces. Here we have a diagram with different forces. We have the force F, which is called the motional force. It is an external force applied to the object in order to move. So, as the object moves, there is a reaction force due to the surface. This reaction force is called friction force. The magnitude of friction force depends on the force called weight. The weight is the force due to gravity. So as the weight increases, more the object is in contact with the surface and more the friction force. So the reaction force of the weight is called the normal force. The normal force is the force that the surface exerts on the object. So by action and reaction, the normal force is equal to the weight in magnitude, but opposite in direction. The magnitude of weight is equal to mass times acceleration due to gravity. And the sum of the two reaction forces, normal and friction force, gives the total reaction force, R. Okay? In summary, the motional force is an external force applied to the object that causes motion. The weight is the force due to gravity, and it is equal to mass times acceleration due to gravity. The weight is always perpendicular to the horizontal, whereas the normal force is the force exerted by the surface on the object. It is the reaction force to the weight of object and has a role of holding together two surfaces in contact. The friction force is defined as a resistance to motion because of the interaction of the body with its surroundings. It is always opposite to the motional force. So we have two types of friction forces: static friction force and kinetic friction force. Static friction force, it is a friction force of object when it is at rest. It is the force which opposes to the start of motion. So this force helps the object to start motion by action and reaction principle. The second type is kinetic friction force. Is the force which opposes to the relative motion of two surfaces in contact. So the kinetic friction force is the friction force of the object when it is moving. So this force helps the object to stop moving by decreasing its speed. The coefficient of friction. Coefficient of friction is the level of the friction of a given surface. So these coefficients depend on the two forces, the friction force and the normal force. So both static friction and dynamic friction forces are directly proportional to the normal force exerted by the surface on the object. So it means that When the friction force increases, the normal force also increases. So the normal and the friction force, they are proportional. When one increases, the other will increase proportionally. And the coefficient of proportionality is the coefficient mu, called coefficient of friction. Thus, the coefficient of friction is defined as the ratio between friction force and the normal force. It can also be defined as the ratio of the force required to move two threading surfaces over each other and the force holding them together. That is friction force over normal force. So the coefficient of friction describes how easily the material slides against another surface. The coefficient of friction also can be obtained by using the angle between the normal force and the total reaction force R. This angle between the normal force and the total reaction force is called the angle of friction. It is called the angle of friction because it depends on the friction force. When the friction force increases in length, when it increases in length, the angle of friction will also increase. When the friction force decreases in length, the angle of friction also will decrease. So this angle depends on the length of the friction force. That's why it is called the angle of friction. So how we are going to get it? We are going to find the tangent of this angle. The tangent of this angle is equal to the opposite side divided by adjacent side of it, by definition. So the opposite side of this angle, it is the friction force. And the adjacent side of this angle, it is the normal force. Thus, the tangent of the angle of friction is equal to the friction force divided by the normal, which is equal to coefficient of friction mu. So we are going to talk about the applications of Newton's laws of motions to solve the problems of dynamics. The first point, you have to read, draw, and label a given problem. The second point, you have to draw free body diagram for each body. You have to choose X or Y axis along motion and choose direction of motion as positive. It means that the forces in the direction of motion will be taken as a positive, and the forces opposing the direction of motion will be negative. So you have to write Newton's law for both axes. Along x-axis, the sum of all forces in x direction is equal to the mass times acceleration in the direction of x. And the sum of all forces in the direction of y is equal to the mass times acceleration in that direction. And from there we get the equation which is going to help us to solve for the unknown quantities which is asked to find. Okay, the first application, we are going to consider the motion of an object along an horizontal plane. Here we have the horizontal plane, and we have the object which is moving in this direction. So to apply the second law of Newton, we you are going to separate two axes. We're going to start with x-axis. Along x-axis, we have the motional force, which is positive because it is along in the direction of the motion. And we have the friction force, which is negative because oppose the motion. So the sum of these two forces must be proportional to the mass times acceleration. Okay, the net force is equal to mass times acceleration. Along the x-axis, we have F, motional force, minus friction force is equal to the mass times acceleration. So from here, you can calculate the motional force. The motional force will be mass times acceleration plus friction force. You can calculate the acceleration of the object. It is motional force minus friction force divided by the mass. And so on and so on. Applying the second law of Newton along y-axis, on y-axis you have two forces, normal force and weight. And the normal is the reaction force to the weight. That means that they are equal in magnitude, but opposite in direction. So normal minus weight is equal to 0 because along y, we have no acceleration. Acceleration in the direction of y is 0. Then the normal force for the object moving on horizontal plane is equal to the weight. It's equal to mass times acceleration due to gravity. So the application of the second law of Newton along the y-axis will help us only calculating the normal force. The second case, it is motion along an inclined plane. So we have no longer horizontal plane, but we are going to shift this x at a certain angle with horizontal. So as x and y, they are perpendicular. If x shifts an angle theta with the horizontal, also y will shift the same angle theta with the vertical. Okay, so the case one is the objects heading up an inclined plane. We have an inclined plane, inclined where x is inclined at angle theta. Automatically, y will be also inclined at angle theta with the vertical. So this angle is going to help us to find the component of the weight. So for this case, the weight will not be used. We are going to use their components. The weight has two components. The components perpendicular to the plane and the components parallel to the plane. So how to get the components? I think everyone knows how to get the components of a given vector. So for the weights, by using this angle theta, we are going to do projection of the weight on y-axis and projection of the weight on x-axis. The projection of the weight on y-axis, we are going to get the weight cosine theta. It is the components adjacent to the angle theta. And the component of the weight on x-axis, it is weight sine theta. It is a component opposite to the angle theta because it is equal to this one. This side is equal to this side. So the weight sine theta, it is opposite component to the angle theta. Then after calculating the components of the weight, we are going to apply the second law of Newton on the x-axis and the y-axis. Along the x-axis, we have motional force, we have weight sine theta, and we have friction force. For this case, where the object is sliding up an inclined plane, the weight sine theta is supporting friction force. It means the weight is opposing the motional force. That's why we need a big force to move up this object to overcome the weight sine theta and the friction force. Along the y-axis, we have the normal force and we have weight cosine theta. Okay, we are going to apply now the second law of Newton along x-axis. We have the motional force, which is positive because it is in the direction of motion, minus friction force because it is opposing the motion force, and minus weight sine theta because it also opposes the motion. This must be equal to mass times the acceleration. Applying the second law of Newton along y-axis, on the y-axis we have two forces, normal and the component of the weight cosine theta. So the normal force minus weight cosine theta is equal to 0 because there is no acceleration along the y-axis. The object is moving in x direction, but not in y direction. So from here, we are going to get the value of the normal force. The normal force is equal to mass times acceleration due to gravity times cosine of the angle theta. So coming back to the x-axis, you can calculate the motional force from this equation. Motional force is equal to mass times acceleration plus friction force plus weight sine theta. You can calculate the acceleration. You can calculate the weight sine theta, and so on and so on. For the case of the object sliding down an inclined plane, for this case, the weight sine theta is no longer opposing motion force, but is supporting motion force. That's why when the object, for example, when a truck which is heavy is moving down on a road, its weight is supporting the motion force and it has tendency to move fast. So in order to decrease the speed, you have to apply the brake so that the truck will not move fast and cause an accident. So it is similar to the previous one. We are going to apply the second law of Newton on the y-axis and the second law of Newton on the x-axis. Along x-axis, we have motion force, weight sine theta. They are both positive, and the friction force, which is negative because it opposes motion. Along the y, we have normal and the weight cosine theta. So applying the second law of Newton along the x-axis, we have motion force plus weight sine theta minus friction force is equal to mass times acceleration. So from here, you can get any force you want. You can calculate motion force is equal to mass times acceleration minus weight sine theta plus friction force. You can calculate acceleration, you can calculate friction force, and so on and so on. So along the y-axis, the normal is equal to the mass times acceleration due to gravity times cosine of the angle theta, like the previous case. The other application is on Atwood machine. Atwood machine is the system made by two unequal masses that are hung vertically over a light and frictionless pulley. We have this system. So here we introduce a new force called the tension. When you have the wires, the reaction force in wires is called tension instead of called normal. So instead of using normal force, we are going to use tension force, because the tension force is the appropriate term used in the wire when you have reaction force. Is the force that the string or wire exert on the object. It is the reaction force of the wire to the applied weight. So as the puller is light, means massless, and has no friction, the tension will be the same. Tension 1 here will be equal to the tension on the other side. And also the acceleration will be the same, because the two masses, mass 1 and mass 2, they are connected. So because they are connected, we move with the same acceleration. To solve this, we are going to use the free body diagram. So the free body diagrams of the masses are shown in figure below, where we assume that mass 2 is greater than mass 1. We have the free body diagram here of two masses, mass 1 and mass 2. On mass 1, we have the reaction force to the weight. The weight is downward oriented, and in the wire, there is a reaction force to the weight, which is upward, called tension. And for the mass 2, we have the weight. The weight is always downward oriented, perpendicular to the horizontal. And the reaction force will be in the opposite direction. But as M2 is greater than M1, we will have this direction of motion. M1 will move up and M2 will move down. So M2 will give the direction of motion because it is greater than M1. Applying the second law of Newton on mass 1, so the tension is in the direction of motion will be positive. Tension minus weight 1, which is opposing motion, is equal to M1 times acceleration. That is T, tension T minus M1G is equal to M1 times acceleration. So that is equation 1. On applying the second law of Newton on M2, we have weight 2 is positive because it is supporting motion. And tension T is negative because it is opposing motion. Now we have weight 2, that is M2G, minus tension T is equal to M2 times acceleration. And we have the second equation. So to get one equation to represent the whole system, we are going to do the sum. We add the equation 1 to equation 2. 1 plus 2 gives this equation. And from here, we are going to calculate the acceleration of the system. So acceleration is equal to the difference of weight, the mass 2 times g minus mass 1 times g. It means it is the greater weight minus the smallest weight, then divided by the sum of masses. Then after getting the acceleration, we are going to replace it into the one of the two equations, and we get the value of tension. So Replacing this value of acceleration in the equation 1, we are going to get this value of tension. Tension will be mass 1 times acceleration plus mass 1 times acceleration due to gravity. When we replace the value of A into the equation 2, we are going to get this. The tension is equal to M2G minus M2A. These and these will give the same value. Example, find the acceleration and the tension in code for the system shown below. Atwood machine. We have this system, the frictionless and the massless fluid, the mass of 2 kg and mass of 5 kg. As we have seen, the mass of 5 kg is greater than 2 kg. That means that the 5 kg will pull the 2 kg. These will move up and 5 kg will move down. Automatically, here we are going to have the weight 2 downward and the tension upward. Here we are going to have weight 5 downward and the tension 5 will also be upward. Solution to this problem, first we are going to apply the second law of Newton to the entire system along the line of motion. The second law of Newton here, we are going to have the tension minus 2 times acceleration due to gravity is equal to 2 times acceleration. That is the first equation. The second equation on 5 kg, the 5 kg times acceleration due to gravity minus tension is equal to 5 kg times acceleration. Here we have a free body diagram. This is what I'm telling you. Tension minus M2G is equal to M2 times acceleration. And M5G minus tension is equal to M5 times acceleration. The first equation and the second equation. T minus MT2G is equal to M2A. The second equation is M5G minus T is equal to M5A. Adding the two equations, we are going to get this. So from this equation, we are going to calculate the acceleration of the system. Acceleration will be the difference of weight, the biggest weight minus the smallest weight, divided by the sum of the both masses. That is 5 minus 2 times 10 over 2 plus 5. We are going to get 4.285 meters per second squared. And replacing this value of acceleration in equation 1 or 2, we are going to get the value of tension. Then from the equation 1, we get tension is equal to M2A plus M2G. That is 2 times 4.285 plus 10. It is 28.57 Newton. Force in circular motion. That is another application. We are going to apply the second law of Newton on the object moving on circular motion. For circular motion, there is an important force required to have circular motion. That is called centripetal force. Centripetal force is a force required to keep a body of mass m moving in a circle of radius r. So you see that without this centripetal force, the circular motion is not possible. And the magnitude of centripetal force is equal to the mass of the rotating body times centripetal acceleration. Remember, from circular motion, the centripetal acceleration is equal to v linear velocity squared divided by radius. And we have centripetal force is equivalent to mass times v squared over radius. Example, a 3 kilogram rock swings in a circle of radius 5 meters. If its constant speed is 8 meters per second, what is the centripetal force? So we have this diagram. We are given the mass of a rock of 3 kilograms. We are given the radius of 5 meters. And we are given the speed of 8 meters per second. We know that the centripetal force is equal to mass times v squared over radius, where centripetal acceleration is v squared over radius. So we have this. Centripetal acceleration is 12.8 meters per second squared. So replacing it into the force, the formula of centripetal force, we are going to have 3 kilograms times 12.8 meters per second squared, equivalent to 38.4 Newton. Working examples. Example number 1. 2 blocks are connected using a non-elastic cord. A cord is a strong wire, as shown in the figure below. If all friction forces are negligible, we have this diagram. The diagram of 5 kilograms and a diagram of 4 kilograms connected together by a non-elastic cord. And on the surface, we have no friction. Calculate the acceleration of the system and calculate the tension in the cord connected, that is connecting the 2 masses. The solution to this problem, we are going to draw the diagram and putting the forces. Here we have the motional force is 30 Newton. As the motion force is pulling this 5 kilograms forward, there is a reaction force in the cord. That is tension 1. Tension 1 is the reaction force to the motional force. And reaching to the second mass, the reaction force, the tension will change the direction and will pull the mass 2 forward. That's why as the mass 1 is moving, the mass 2 also will follow because of this tension. As there is no friction on the surface, the 2 tensions will be the same. And as the 2 masses are connected, the acceleration is also constant. Okay, applying the second law of Newton, on mass 1 and the second law of Newton on mass 2, we are going to have the following equations. On M1, the force F minus tension T, T1, which is equal to T, is equal to M1 times acceleration. Because on this mass, we have only 2 forces. The force F, which is positive because it is in the direction of motion, and the tension, which is negative because it is opposing motion. That is the first equation. On mass 2, we have only 1 force. We have only tension. So the tension force is equal to mass 2 times acceleration A. So we have 2 equations. We are going to sum these 2 equations to get one equation to represent the system. We are going to have F is equal to M1 plus M2 times acceleration. Now, this equation is going to help us to get the acceleration of the system. The acceleration of the system is equal to force F divided by mass 1 plus M2, which is equal to 3.33 meters per second squared. Replacing the value of acceleration in either the first equation or the second equation, we are going to get the value of tension. So in reference to the above blocks equation 2, we have tension T is equal to M2 times acceleration. That is the second equation. Replacing the value of A into this equation, we are going to have the tension of 13.32 Newton. The second example, the figure below shows a box of dirty money of 3 kilograms. The mass 1 is 3 kilograms. It is on a frictionless plane. The plane has no friction, and it is inclined at 30 degrees. The angle θ1 is equal to 30 degrees. The box is connected via a cord of negligible mass to a box of rounded money of 2 kilograms. The mass 2 is 2 kilograms on a frictionless plane that is inclined at 60 degrees. The angle θ2 is 60 degrees. The pulley is frictionless and has a negligible mass. Then calculate the acceleration of the system and calculate the tension in the cord. So to solve this, we have to apply the second law of Newton on mass 1 and the second law of Newton on mass 2. Remember that the second law of Newton states that the sum of all forces acting on the mass is proportional to the mass times acceleration. So we are going to get the equation from this mass and the second equation from the mass 2. So to solve this, we have to draw the diagram with all forces acting on the masses. So let's start with the first mass. For the mass 1, we have the weight. The weight of mass 1 is equivalent to m1 times acceleration due to gravity. This weight is always perpendicular to the horizontal. So the weight will not be inclined, but as the mass 1 is inclined at 30 degrees, the weight 1 will have 2 components. One component will be perpendicular to the plane, and the other component will be parallel to the plane. So how to get these 2 components? To get the components, we are going to use the angle θ1 of the inclination. Now, before the inclination, the x-axis was horizontal. So for mass 1 to be inclined at 30 degrees, the x-axis is shifted also at the same angle, 30 degrees, from horizontal to this new position. Then, as x-axis shifts, the y-axis also will shift the same angle because x and y are perpendicular between them. If x does a displacement of 30 degrees with the horizontal, the y-axis also will do the same, will do displacement of 30 degrees with the vertical. And this angle between the y-axis and vertical or weight will help us to find the component of the weight. So the one component of the weight, it is weight 1 cosine theta 1. It is obtained by projecting the weight 1 on the y-axis. I think all of you know how to do projection of a vector. From the head of weight 1, we do projection on the y perpendicular to it, and we get this component, weight 1 cosine theta 1. It is a component which is adjacent to the angle theta 1. The second component, it is weight 1 sine theta 1. So it is obtained by projecting the weight 1 on the x-axis, perpendicular to it. Then these components, it is weight 1 sine theta 1, which is the opposite component to the angle. Because this component, weight 1 sine theta 1, it is parallel to this line. And this line is opposite to the angle theta 1. Okay, now, all forces acting on the mass 1, we have the weight 1 sine theta 1, that is pulling the mass in this direction, downward. So due to this pull, we will have the opposition in the wire, in the cord. The reaction force is the tension. Tension 1 is reacting to the pull, weight 1 sine theta 1. And we have the weight, the component of the weight, that is perpendicular to the plane, weight 1 cosine theta 1. This component is equal to the normal force. The normal force is the reaction to the weight 1 cosine theta 1. On the second mass, it is also the same. We have weight 2. The weight 2 is also perpendicular to the horizontal. As the mass is increased, the weight will stay in the same position, will not be increased. But we will have the two components of the weight 2. One component of the weight 2, it is weight 2 sine theta 2. Weight 2 sine theta 2 is obtained by projecting weight 2 on the x-axis. From the head of weight 2, we do projection on x-axis perpendicular to it. And the component obtained is weight 2x, which is equivalent to the weight 2 times the sine of the angle theta 2. The same, the second component, weight 2 cosine theta 2, is obtained by projecting weight 2 on y-axis. And we get the component, weight 2 cosine theta 2, which is adjacent to the angle theta 2. The angle theta 2 is here because the x-axis before the inclination was horizontal. After inclining this plane at the angle theta 2, the x-axis will have this position, and the y-axis will have this position. So the displacement between the two positions, the old position of y before inclination was this, and the new position after inclination is this. So the angle between the two is theta 2. It is equal to the angle between the new position of x with the old position of x before inclination. The old forces acting on mass 2 are, we have weight 2 sine theta 2, pulling the mass 2 down in this direction. And we will have the reaction force in the cord, in the wire. That reaction force in the wire is tension T2. The tension T2 is opposing to this pull, weight 2 sine theta 2. Then, applying the second law of Newton on mass 2, we will have weight 2 sine theta 2 minus theta 2 is equal to mass 2 times acceleration. Okay, so, but before applying the second law of Newton, we have to determine the direction of motion to know which force will be positive and which force will be negative. The direction of motion is determined by the two components of the weight, weight 1 x and weight 2 x. The biggest component between the two, it is the one which will determine the direction of motion. So let's calculate weight 1x. Weight 1x is equal to 3 kilogram times 10 meter per second squared. This is acceleration due to gravity times the sine of the angle 30. The angle 30 is theta 1. And that is equivalent to 15 Newton. Weight 1x is equal to 15 Newton. So let's calculate the second component, weight 2 sine theta 2. Weight 2x is equal to 2 kilogram times acceleration due to gravity times sine of 60 degree. It is equivalent to 17.32 Newton. So you see that the weight 2x is greater than weight 1x. It means that the weight 2x will pull weight 1x. And thus, both boxes will move in clockwise direction as weight 2x is greater than weight 1x. We have these movements. The direction of motion will be this. Now, this will help us to apply the second law of Newton, because now we are able to determine the positive forces and negative forces on both masses. Starting by mass 1, we have tension 1 is in positive minus weight 1 sine theta 1 is equal to mass 1 times acceleration. We are going to use the forces in the direction of x because the object is moving in the direction of x. There is no motion in the direction of y. Now, tension 1 is equal to tension 2 because the pulley is frictionless and massless. Also, acceleration A1 is equal to the acceleration A2 because the two masses are connected. It means that the two masses are moving with the same acceleration, with the same speed. Okay. Now, we are going to have these two equations. Tension minus 15 is equal to 3 kilogram times acceleration. That is equation 1, obtained by applying the law of Newton on mass 1. Applying the second law of Newton on mass 2, we are going to get 17.32 minus tension is equal to 2 kilogram times acceleration. Remember, 15 is weight 1x, 17.32 is weight 2x. So to get the acceleration of the system, acceleration A, we are going to add equation 1 with equation 2. To get one equation to represent the system and there we're going to get acceleration A. So by adding the two equations, we are going to get 17.32 minus 15 Newton is equal to 3 kilogram plus 2 kilogram times acceleration. And then acceleration is equal to 2.32 Newton divided by 5 kilogram, which is equal to 0.464 meter per second squared. This is the acceleration of the system. After getting the acceleration of the system, we are going to replace it in the one of the two equations. So let's replace the value of A in the equation 1. We are going to get tension equal to 3 kilogram times acceleration plus 15. Finally, we get the tension equal to 16.4 Newton. The tension in the wire pulling the two boxes. Thank you for watching. Remember to subscribe, like, and share. See you next time.